This is your fourth video for production of materials, and it's on cellulose. Let's just quickly review addition polymerization. So in this reaction we're going to have two monomers, and these are two monomers of ethylene, and when we bond them together you can see that the double bond breaks, so these double bond breaks, and then we create a single bond between the carbons, and we create this really long chain. So you can see that they're just plugging end to end. The chain goes on and on and on, and there are no molecules lost, and there are nothing's floating around or anything like that. So let's have a look at a new type of polymerization. Condensation polymerization. Now it follows the same principles in that monomers will form polymers, but it's a little different in that, unlike the addition polymerization where they just plug in end to end, when these monomers plug together, a small molecule is going to be lost. And most of the time for the molecules that we'll deal with, we're going to lose a bit of water. So that's why we call it condensation. So let's have a look at an example. So here we have two monomers of glucose, and in particular we have beta glucose. We call them beta glucose because these hydroxyl groups here point in different directions. So as you can see, this one kind of points downwards and this one's kind of sticking upwards in this direction. So that's the beta. The alpha on the other case would have both of them pointing in the same direction. So like this OH group would be hanging, like it would be over here. So these two would sort of be on the same end. But again, that's just, I'll just rub that out. That's just a bit of side knowledge for you. So again, here we have two monomers, both of them are glucose, beta glucose, and they are going to attach together. Now remember, a small molecule is lost in a condensation polymerization reaction. So when we have a look here, we have these two hydroxide groups that are near each other, and as you can see, you can sort of see where the water is going to come from. So this OH with this H is going to ping off and form our H2O, and this carbon bond is going to come over here to the oxygen, and that's how these glucose monomers are going to fit together and provide a polymer called cellulose. Now cellulose is something that we're really going to focus on a lot in this topic, but again, just to go back to your alpha glucose, if you have monomers of alpha glucose and they plug together, again, same manner where the OH group and one of the H's for the other hydroxyl group are going to bond together and create water. And then again, the carbon will bond to the oxygen. So it's the same exact process, just the OHs are in a different position. So when alpha glucose monomers come together, they'll actually create starch. So they will create two different forms of polymers. So in this case, we're focusing on cellulose. What I'd like you to do now is pause the video and draw out these beta glucose molecules, showing how the condensation polymerization occurs. Cellulose makes up the cell walls of a plant. So there are four things that we need to know that really are key properties in terms of its structure. So the first one I want to have a look at is the fact that it's insoluble. Now when we had a look at the condensation reaction, we saw that we were releasing a hydroxyl group. So I'll just get my pen working here. So we're releasing a hydroxyl group. The less hydroxyl groups we have, the more insoluble the polymer becomes. And having cell walls that are insoluble is great so that the plant isn't sort of dissolving in itself every time it has a drink. The next thing I want to have a look at is the 1,4-beta glycosidic bond. And this is just about how the polymer is structured and how it actually bonds together. And that has to do with the numbering of the carbons. So if we have a look here, I'll go through and name the carbons. So 1, 2, 3, 4, 5. And on the second polymer, it sort of goes in the opposite direction. And 1, 2, 3, 4, 5. And then again, same way for the next one. 1, 2, 3, 4, 5. So you can see here where the 1 and the 4 is coming from. The bond between the beta glycosidic. Now, beta glycosidic is just sort of implying that it's beta glucose monomers bonding together to form a polymer, so that's a glycosidic bond, and the 1,4 is telling you which carbons it's happening on. So here, 1 to 4, 1 to 4, and that's basically it. The third point is that it creates straight chains, and I'll just change colour here because I'm getting a little messy. The reason that the polymer forms straight chained are these extra carbon groups that are attached to the glucose. Now we'll go into detail about them a little later, but all you have to know for this in terms of its structure and how it looks is that these groups are located on opposite sides. So you've got one up, one down, one up, one down, one up, one down. And because it is so evenly distributed on alternating sides, it's going to create a nice straight chain. And again, being that it makes up the cell wall of a plant, it needs to have that straight, rigid structure. And so the fourth point is that the fact that glucose or cellulose in terms of its polymer are very, very strong. And that has to do with a hydrogen bond. So I've put in a second polymer chain here just to show you where this bond is coming from. And it's happening between the OH group here to this OH group here. So it just wants to hang on, just sort of, be my buddy. Again, remember with hydrogen bonds, it's not officially a bond, it's more like an attraction. I'm just checking you out, what's going on over there. So this pull and this draw with the hydrogen bond keeps all the polymer chains really tightly packed and creates a very strong, rigid structure. So again, think back to a plant. Plants don't have bones. They're getting their strength and rigidity from the cellulose structure itself. So it needs to be insoluble so that the water isn't penetrating the actual cell wall itself, so that the plant sort of isn't dissolving in itself. It needs to have straight chains. Straight chains are going to give it its rigidity and strength. And on top of it, it's really strong because it has those hydrogen bonds keeping all the polymer chains nicely, tightly packed. And just as an added, to know how these bonds are joined together, it's through a 1,4-beta glycosidic bond. So it's basically just telling you that the bond is happening between the first and the fourth carbon on alternating monomers. So take notes of this. We'll be doing a practice question in class.